Hey everybody, it's Monday, May 3rd, and as you can see here in the aim today, our goal for today's video is to review the free response question that was given to you on Friday. Now, I like this question. I think it combines a number of skills that are required for the AP test. They ask you first to consider some conceptual stuff, then to derive an equation, then to evaluate the results of your derivation, but also because it mixes topics well also. You get a little bit of this ramp stuff with a little bit of projectile motion, and that I really think makes this an excellent question, a good representation of some stuff you could expect to see on the AP test. So let's get into it. This problem here says a student releases a block of mass m from rest at the top of a slide of height h1. The block moves down the slide and off the end of a table of height h2, landing on the floor a horizontal distance d from the edge of the table. Friction and air resistance are negligible. The overall height h of the setup is determined by the height of the room. Therefore, if h1 is increased, h2 must decrease by the same amount so that the sum h1 plus h2 remains equal to h. The student wants to adjust h1 and h2 to make the distance d as large as possible. Now, that part is very important, that these two things always have to add up here so that they remain the same value, because essentially what you're going to see here is this is all about trade-offs. If you try to decrease one height, you got to increase the other, and ultimately that's going to affect the quantities which are relevant to determining the range, or at least that's what you were supposed to realize. So the first part of this question here says, without using equations, explain why making h1 very small would cause d to be small, even though h2 would be large. So notice here, if instead of making this problem like this, where h1 was this height, if instead the ramp, was just maybe this small, that means h2 would be this entire distance here then. And so by making that height small, again, you make that height big. Now, the point here is there are two things that determine the distance, the velocity and the time. And so because they're asking you about changing both of these heights, really, even though it mentions you're just making h1 small, that also involves making h2 larger. It's a smart idea to mention both of these things. Now, of course, the good thing here, without using equations, you really want to make sure you pay attention to that, because if you're only talking about the equations, then you're not going to get any of the points. But the idea is you got to explain both parts of this in order to get the credit. And so what I wrote here for the answer is the range of a horizontally launched projectile depends on both its horizontal launch velocity and the time it spends in the air. While increasing the height h2 will make the time in air larger, if h1 is kept small, the block won't gain as much speed when sliding down the ramp. The smaller gravitational potential energy loss will result in a smaller kinetic energy gain, which means the horizontal launch velocity will be less. Since the range is dependent on both the horizontal launch velocity and the time it spends in air, a small launch velocity will make the product of the launch velocity and the time small. Now, obviously there at the end, I did mention a little bit about the equations, that the product of those two things is going to be small. You don't have to do that, but I did it because I'm used to discussing things in the context of equations. Clearly, they're not going to take away any points from you by talking about that, because if you cover the points they are giving you credit for, then they're not going to subtract any because you happen to mention the product of those two things. Take a second to pause this video here and take a good look at this explanation, making sure you understand all parts of it. Maybe add whatever you think might be missing from your own explanation. And when you hit play, we'll move on to the scoring guide. All right, moving on to the scoring guide here, we see this part of this question was worth 2 points. You got the first point for recognizing a small horizontal velocity for the block at point P. And just to be clear, the horizontal velocity at point P, they're just saying the edge of the table, that's where point P is. And the second point is for stating or implying that the block doesn't go very far, even though there is a longer fall time. And so basically, you got to say, yeah, the time is bigger, but because the horizontal velocity is going to be so small, range isn't going to be very big. That's the basic idea. Take a second to pause this video here and review this part of the scoring guide, making sure you understand all aspects of it. And when you hit play, we'll move on to part A2. All right, moving on to part 2 here. Part 2 says, without using equations, explain why making H2 very small would cause D to be small, even though H1 would be large. And so, of course, here, now we basically just have the first question in reverse. Instead of what we just showed before, they can make this thing really large and then just make H2 tiny. And so what I hoped you realize when you were going over this is that this is just the exact opposite explanation that you need to give for this part of the question. So what I wrote here is the range of a horizontally launched projectile depends on both its horizontal launch velocity and the time it spends in the air. While making H1 larger will make the horizontal launch velocity of the block larger, if H2 is kept small, the block will spend less time in air. The time a horizontally launched projectile spends in air depends on the height. If the height from which the block is launched is smaller, the block will spend less time in air. Since the range is dependent on both the launch velocity and the time it spends in air, a smaller time in air will make the product of the launch velocity and the time small. Now, of course, that product of the launch velocity and the time discussion at the end of this doesn't really matter as far as earning the points, but I included it to make my answers at least similarly worded. Take a second to pause this video here and review this explanation, making sure you understand all parts of it. Of course, add anything to your own explanation if you feel like it's missing. And when you hit play, we'll take a look at the scoring guide. All right, moving on to the scoring guide here, we can see that they gave you 1 point for recognizing a large horizontal velocity for the block at point P, that's at the edge of the table, and then for mentioning a short time of flight for the falling block. So the example explanation here they gave says, now the block gains a lot of kinetic energy on the ramp, so it leaves the table with a large horizontal speed, but the small H2 means the block spends so little time in air that it lands before covering much horizontal distance. Take a second to pause this video here and review this part of the scoring guide, making sure you understand all aspects of it. And when you hit play, we'll move on to part B. And that brings us to part B. Part B is my favorite part of this question. It is the reason why I gave this to you. It says derive an equation for D, the horizontal range here, the horizontal distance or the range, in terms of H1, H2, M, and physical constants as appropriate. All right. The first thing to realize about this derivation is, again, if you are going to determine the horizontal range here, that horizontal distance, dx, you need the launch velocity in the x direction, and you need the time. And so essentially what we have to do here is figure out what the speed is going to be when the block gets here, once it goes down the ramp, and then get an equation for the time once it leaves the side of the table and ends up, being launched. So what I hoped you realized, at least at first, is in the beginning, this is a ramp. And they are telling you the height of the ramp. It should be clear to everybody by now, unless it's an inclined plane and the question is asking you about acceleration, you should be talking about energy conservation for ramps. And so the first part of this is going to be energy conservation. At the top, the object has a gravitational potential energy, and at the bottom, the object has kinetic energy. So what we're going to do first here is we're going to say the initial gravitational potential energy at the top of the ramp is going to be equal to the final kinetic energy of the ramp. Now, of course, you can do this whichever way you want. I think what I like to do personally, so I don't screw myself up, is I like to do the derivation in terms of symbols that we always use. So there's like symbols in the reference table, whatever. And then at the very last line, I like to sub in the symbols that they're giving you for the variables in the specific problem. I want you to keep that in mind as I'm going through this, but of course, I will tell you what I mean again when we get to these parts. So the first thing I'm going to do here is I'm going to sub in my equation. So the initial gravitational potential energy is going to be given by the equation mg delta y, and the final kinetic energy is going to be given by the equation 1/2 mv squared. And so the first thing you do here, I think, or the first thing to recognize, is that the mass does not affect the final speed. We've been talking about that forever. And so when you solve this for this final speed here, you end up just getting 2g delta y, a pretty familiar equation, I hope, from conservation of energy. if you are doing a potential to kinetic conversion problem and you're looking for the final speed, that's always going to be the equation. Now, of course, in this particular situation, they're telling you the height through which this thing is falling while it's converting its gravitational potential energy to kinetic energy is h1. And so this is what I meant before. Now that I have the equation for my final speed, square root of 2g delta y, I'm going to say, well, in this particular problem, the height they are talking about there is called h1. And so I'm going to resub that in here as the square root, v equals the square root of 2g h1. And that's my equation for the final speed. Now, of course, I'm not done yet, because as we mentioned, the range is based on two things. I've got the final speed part. Now I need to do the time part. And so the time here, I would hope, is pretty straightforward to everybody by now. For a horizontally launched projectile, the horizontal motion is independent from the vertical motion. And so to find the time, you only need to use information from the vertical direction. Well, because this part of the table is level here, the initial velocity in the vertical direction is going to be 0. Of course, we know that the acceleration is just going to be negative g here. And, well, we also know that the displacement is just going to be this height here, h2. Now, of course, we can call that negative h2. As we always end up seeing anyway, when you're going to solve for the time, the negatives cancel because, of course, time is never going to be negative. So we don't need to go too nuts about the signs. But that's the basic idea. Whenever we solve for the time for a horizontally launched projectile, we use the equation delta y equals v naught yt plus 1/2 ayt squared. Now, of course, because this projectile is launched horizontally, the v naught y term goes to 0. And so what we're left over with is delta y equals 1/2 ayt squared. And now when you solve this for t, you end up getting t is equal to the square root of 2 delta y over ay. Now for this next step, we're going to make two substitutions. The first substitution is going to be delta y, at least in this part of the problem, now is equal to the height from which this thing was launched. So that's h2. And we're going to say here that a, y, at least has a magnitude equal to g. And so because both of those things are true, then our time equation is going to end up being t is equal to the square root of 2h2 over g. And of course, we're still not done, because we have to ultimately do this to derive an equation for the distance. But now we have all the pieces. According to the equation for the horizontal range, we have to take the horizontal velocity and multiply it by the time. Since we have an equation for the horizontal velocity and an equation for the time, we could just do that right now. Now, whether or not you would have actually needed to write this part of the equation with the 1/2 axt squared, I'm not really sure. I don't think so is the answer. It seems like they'd let you get away with that. It doesn't really matter. The acceleration is 0. But I'm just going to go ahead and show that crossed out to acknowledge that I know that. And once again, here we have the equation then, dx equals v naught x times t. And so when I go through to plug that in now, I'm going to take my equation for v naught x, which is the square root of 2 times g times h1. And I'm going to multiply that by my equation for the time, which is the square root of 2 times h2 over g. Now, whether you realize this or not, it is very important to remember that you can always take the product of square roots and say that that's equal to the square root of the products. Essentially, what I'm saying here is you can just gather everything here underneath the radical. That's the point. And so the next line of this derivation should read like this. Everything that's in the numerator stays in the numerator. So I have 2g h1 h2. And then in the denominator, or of course, I don't want to forget about my second 2. And in the denominator, I have g. And so cleaning this up a little bit, notice, which is very interesting, the g's cancel, and I just have dx equals the square root of 2 times h1 times h2 times 2. Now, of course, 2 times 2 is 4. So I can sub that in and write 4 H1 H2. And if I really want to simplify this thing, which I don't know if it's necessary for the points, but just to do it, the square root of 4 is 2. And of course, if the square root of the products is what we have here, then we can also say that's the products of the square roots. So we can have the square root of 4 times the square root of H1, H2. And of course, the square root of 4 is 2. So my final, most simplified expression here is 2 H1, H2. That's equal to dx. And that's it. Take a second to pause this video here and write that down, making sure you understand all aspects of this derivation. And when you hit play, we'll move on to the scoring guide. All right, now moving on to the scoring guide here, they did this in a little bit of a different way. It's mostly the same, though. You get 1 point for using an energy conservation statement. So that corresponds to step 1 here, basically by saying mgh is equal to 1/2 mv squared, and then solving for v1. Notice here, they're calling v1 the launch speed at point P. I think that makes some sense. It doesn't really matter to me, but they're basically saying the speed it reaches after it goes through that height h1 is equal to a speed they're calling v1. Big deal. They're giving you 1 point for setting up a time of flight calculation using vertical acceleration. Then it says corresponds to step 2a in the example below. So that would be using a kinematic equation here. Find the time of flight using the independence of the horizontal and vertical motion. Since the block leaves the table with 0 vertical speed, the vertical kinematic equation y equals y naught plus vy naught t plus 1/2 ayt squared reduces to h2 equals 1/2 gt squared, taking downward as positive. Notice you could take downward as negative, and the negative signs are just going to cancel, big whoop, and you get t equals the square root of 2h2 over g. The last step is for using vt equals d. Now, of course, when we were doing that in class, we were saying dx equals vixt plus 1/2 axt squared, and then crossing off the 1/2 axt squared part. But either way, you just had to use that equation to try to find the distance traveled. And so what they showed in step 2b is you just literally take the two equations and multiply them by each other. They say, since there are no horizontal forces exerted on the block, its horizontal velocity stays constant at v1. Of course, that's true. So the block travels a horizontal distance of 2 times the square root of h1, h2. Honestly, if you just left it as this, it seems to me like that satisfies the scoring criteria. But you should always try your best to simplify. Take a second to pause this video here and take a good look at the scoring guide, making sure you understand all aspects of it and evaluate what you would have earned for this part. And when you hit play, we'll move on. All right, now moving on to part C. Part C is a question we haven't seen in a while. I do think it is an interesting question. They could bring it back. They did ask it in practice exams more than once, so I do think it is something to look out for. Basically, after they do ask you to do a derivation, they want you to talk about your derivation. That's something that's going to happen. And so it says here for C1, write the equation or step in your derivation in part B, not your final answer, that supports your reasoning in part A1. Briefly explain your choice. Now, of course, it would be good to remind everybody what the reasoning for A1 was. And the reasoning for A1 was that, a time in air could be large, but a small h1 means you have a small speed. Now, going back to the derivation, where do we see anything that would show a small h1 produces a small speed? It's here. It shows that the speed is directly proportional to the square root of h1. That part of the derivation shows a small h1 is going to give you a small speed. And so here, for this part in C, we can say in the energy conservation part of the derivation, when we solve for the final speed, we see the final speed is directly proportional to the square root of the height. Now, obviously, in our derivation, we label that h1. I think it's perfectly fine for you to label it either way. It says this line of the derivation shows when the height through which the object drops gets smaller, the final speed of the object gets smaller. This makes sense because a smaller change in gravitational potential energy will result in a smaller change in kinetic energy. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, take a look at the scoring guide. All right, moving on to the scoring guide here, we see that this part was worth 2 points, 1 point for mentioning a correct equation or step of reasoning. It should be clear to everybody that that's during the energy conservation part. And then 1 point for correctly explaining why this equation or step mirrors the reasoning of A1. As they wrote as the example, my energy conservation reasoning, part B, step 1, mirrors my reasoning that a small ramp height corresponds to a low potential energy, which is converted to a low kinetic energy, and hence a low speed. Basically, if you talk about how that equation shows small height 1 means small speed, that's pretty much it. That gets you the points. Energy conservation is the key to this one, essentially just because they're talking about the part with the ramp. Take a second to pause this video here and review this part of the scoring guide, making sure you understand all aspects of it. And when you hit play, we'll move on to part C2. All right, moving on to part C2 here. This part says write the equation or step in your derivation, part B, not your final answer, that supports your reasoning in part A2. Briefly explain your choice. Now, of course, just like we did before, I'm going to come back here. What did we say in part A2? Well, in part A2, actually, let me just show the scoring guide. Remember, part A2 was all about how, yeah, the horizontal velocity of the block is going to be large, but if the time of flight is small, then the range is going to be small because the range depends on the time of flight. And so here, I think it should be clear to everybody, this is coming in the time part. As I wrote here in the time of flight part of the derivation, when we solve for the time of flight, we see the time of flight is directly proportional to the square root of the launch height. Now, of course, if you wanted to write there t equals square root of 2h2 over ay or something like that, that's fine. And then I wrote, since the time of flight is directly proportional to the square root of the launch height, we can see that if we decrease h2, the time will get smaller. That's the point here. Take a second to pause this video here and write that down, adding any part of this that may be missing from your own explanation. When you hit play, we'll move on. All right, moving on here. The scoring guide for this part gives you 1 point for mentioning a correct equation or step of reasoning. It's in the time of flight part. That should be clear. And the second point is for correctly explaining why that works here. And of course, the time of flight calculation shows t is directly proportional to the square root of h2. So smaller falling distance, smaller flight time. Pretty straightforward, I think. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. Give the points to yourself, evaluate your own response. And when you hit play, we'll move on to the last part. All right, moving on to the last part here. Part D says, if the experiment is repeated on the moon without changing h1 or h2, will the new landing distance d be greater than, less than, or the same as the landing distance when the experiment is performed on Earth? And then they give you the options greater than, less than, or the same as. Now, every single time I've done this in class, a lot of people, like the vast majority of each class, has gone through this explanation without referring to the equation that they derived in the previous step. It's important to realize that makes no sense. The whole idea here is that if they ask you to derive an equation, it's because they want to ask you about it later. And whether you realize it or not, your equation directly tells you the answer to this question is that it's the same distance. Now, that's a little counterintuitive, I think. It's kind of weird, but I think it's worth discussion nonetheless. The first thing we'll say here is the range would be the same. According to our derivation in the previous part, the acceleration due to gravity in the equation cancels, which shows the range has no dependence on the acceleration due to gravity. I think that works just fine. That's a perfectly reasonable explanation. Now, having said that, I think it is important to understand why that's true. Why that's true has to do with thinking about this problem in two parts. The two parts that the question was inviting you to think about the whole time. It's an energy conservation ramp part, and it's a projectile motion part. Well, what if we just considered the ramp part? How would the acceleration due to gravity affect the problem there if we just considered the ramp part. Well, according to this equation here, the final speed at the bottom of the ramp is directly proportional to the square root of g. And so what that says is the smaller acceleration due to gravity on the moon is going to mean a smaller velocity at the bottom of the ramp. Now, what the time equation shows is the time is inversely proportional to the square root of g. So a larger acceleration due to gravity is going to produce a smaller time. So yeah, the larger acceleration due to gravity does bring the block down to the ground quicker. And I think usually everybody realizes that. And that's why they think the range is going to be shorter. It also gives the block a smaller horizontal launch speed. And I guess we could say the amount smaller the launch speed is the exact same amount the time is bigger by. And I really think that's the point. It has this kind of cancellation effect. So what I wrote is, for the second part, and you didn't need to write this for the answer, I wrote this for you. This makes sense because even though it'll take gravity longer to bring the projectile to the ground when it's launched off the side of the table, it also gains a smaller speed when it goes down the ramp. Those two factors combine to produce the same range. Take a second to pause this video here and write that down. And when you hit play, take a look at the scoring guide. All right, moving on to the scoring guide for this part here. The scoring guide says you get 1 point for the answer the same as, and they score your explanation regardless of the checkbox. And it says the point can be earned if the response is consistent with the answer in part B. So you get 1 point for reasoning that is consistent with the functional dependence of the part B answer. All right, so let's be clear about that. The actual answer to this question is D does not depend on G. So doing the experiment on the moon makes no difference. The increased time of flight, weaker gravity makes the block take longer to make it land, compensates for the small speed gained by a block on the ramp. Now, let's be clear. If you checked greater than, then the G must be in the denominator of your equation in part B. If you checked less than, then G must be in the numerator in your incorrect equation for part B. Basically, this question was all about evaluating the result of your derivation. And this is why it was driving me crazy that so many people were answering this without talking about the equation. Because even if your equation is wrong, they were willing to give you the point if you just used the equation to talk about how, like, the proportionality in the equation dictates the answer. That's a super important thing to realize as far as the test is concerned. I said it once, I'll say it again. When they ask you to do a derivation, it's because they want to ask you about it. It's important every question after the derivation for you to keep the derivation in your head. Take a second to pause this video here and evaluate this scoring guide, making sure you understand all parts of it. And when you hit play, we'll move on. All right, everybody, that is it for today. I hope you enjoyed this problem. I do think it is a good one. I hope you got something out of watching this video. And now you can go ahead to AP Classroom and score your response so we can find out how many points you would have earned for this question. All right, everybody, have a good one.